You have recently learned about the formulas for three different forms of energy: kinetic energy, gravitational potential energy, and elastic potential energy. But where do these formulas come from? You may have seen derivations of these formulas in your textbook that rely purely on algebraic means. I would like to show you how we can derive them graphically. Each of these equations are actually based on a single concept, that the work performed on an object or system is equal to and responsible for the change in total energy of that system. It's useful to remember that work can be calculated with a formula. Work is, of course, the product of the force parallel to motion and the displacement of the object. It can also be shown visually as the area under a data curve of the force acting upon an object versus that object's position along an axis. This graph, for example, could represent the combined amount of force that this team of 4 athletes applies to their bobsled as it moves forward. When we show an area like this, it's really just a visual representation of finding the product of the quantity on the y-axis and the change in whatever quantity is on the x-axis. In this case, the product of force on the y-axis and displacement on the x gives us work done on the bobsled. Also note that when we say under, what we actually mean is between the data curve and the x-axis. Area segments below the x-axis would represent force against the direction of motion and would subtract from the total quantity of work. The resulting work can then be set equal to the change in energy of a system. Here we're about to see a force due to the activation of a fire extinguisher acting upon a system consisting of a student and a wheeled cart. The force and displacement vectors will be shown. The force acts over a displacement d. Notice how the cart speeds up while it's being acted on by the force. Watch again. This time we'll add a graph of the force on the system versus its position. On the graph, the area under the data curve is equal to the work done. Along the base of this rectangle, we have a value d. From kinematics, the distance covered by the cart is equal to 1/2 acceleration times the square of the time interval, assuming the object started from rest. For reasons you'll see in a moment, we choose to replace the acceleration with its equation definition, delta v over delta t. On the vertical axis, we label the constant force as m times a, resulting from Newton's second law, and then we replace a with delta v over delta t. So we can consider the height of this rectangle as being a value m times delta v over delta t. The equation of any rectangle is base times height, so if we multiply the base of this rectangle, 1/2 delta v over delta t times t squared, by its height, m delta v over delta t, we see 2 delta v's on top, a delta t squared in the numerator that cancels with 2 delta t's in the denominators, which reduces to 1/2 m delta v squared. Since all initial values of time and speed in this scenario are 0, we can remove the delta. Now we can see our familiar kinetic energy equation. The work done on the system was equal to and responsible for the increase in its kinetic energy. What about gravitational potential energy? Say we have a forklift raising a crate of mass m through a height change of h. When we lift a heavy object at constant velocity, recall that the force required to do so is equal to the weight of the object, m times g. In this animation, you may have noticed that the crate actually speeds up halfway through the height and then slows down for the remaining half. Watch again. If we graph the vertical force used in lifting the object versus its displacement, we get this. Notice that the force is a bit larger than mg when the box is speeding up, and a bit less than mg when it was slowing down. It's reasonable to say the average force here would just be mg. Were we to lift at constant velocity, it would be exactly mg the whole time. Let's pretend that was the case. So we've labeled the nearly constant force F with mg, and now we can label the displacement h, since the height the crate moved through is the same as the displacement. Now we have some new variables to work with. The rectangle has base h and height mg, so the area and thus the work done on the crate Earth system is h times mg, or mgh. This is where the formula for gravitational potential energy comes from. It should be noted that even if the forklift moves horizontally during this example, first speeding up and then slowing to a stop, the results don't change at all. Instead of multiplying the force component in the direction of motion by the displacement vector, we can instead multiply the displacement vector component that's in the direction of the vertical force. So only the height change matters because all horizontal motion is perpendicular to the force and is therefore irrelevant. Lastly, we can ignore any horizontal friction forces on the crate because these forces only act to change the kinetic energy of the cart throughout the example, first increasing it, then decreasing it, for a net change of 0 anyways. Combining these concepts helps us to see that changes in gravitational energy will always be equal to m times g times the change in height, regardless of the actual path taken by the object, and regardless of any speeding up or slowing down that the object undergoes. Lastly, we have the simple case of stretching out a spring. When we pull on the end of a spring, the force required to do so changes proportionally to the stretch distance. Let's add a graph of the force we use to stretch it out versus its stretch distance. Once again, we will use the concept that the area under the data curve of this graph is equal to the work done on the system, which in this case is the spring. This time, however, the force is varying with the distance. Hooke's law lets us replace F max with k times x. We can leave the base of this triangle alone and let it just be what it wants to be, a variable x. The formula for the area of a triangle, which we have here, is 1/2 base times height. So 1/2 base x times height kx gives us 1/2 x times kx, which gives us 1/2 kx squared. It's good to know that these three formulas actually come from the same concept, which helps us to synthesize the information we've been given about work and energy.